Well, it's a great pleasure to have this opportunity to bring to you our work on revealing the origin of mass in the universe. What I'm going to do over the next few minutes is take you for a walk through the kind of research that we're doing in quantum field theory. Supercomputing plays a very important role in our research program, and so we're going to spend a lot of time talking about the top 500 supercomputers and understanding the way in which the Australian supercomputers fit into this top 500 index. I'll then take you for a tour of some of our most recent results and perhaps show you things about the world in which you live that you've never seen before, experienced before. So what I'm going to do is ask you to leave your everyday experiences behind at the scale of the order of 10 centimeters. We're going to go past nanoscience and realms of chemistry, past the structure of the atom. We're going to look at the atomic nucleus, at the heart of the atom. And even better, we're going to go smaller than that. We're going to look at the individual protons and neutrons, collectively called nucleons, and understand their structure in terms of the most fundamental degrees of freedom, the quarks and gluons of quantum chromodynamics, or QCD for short. QCD is the most fundamental theory that describes how quarks, which are the building blocks of matter, interact with each other through the exchange of gluons. They're very much the glue that binds quarks together in forming visible matter, the matter that we see in our universe. What we're trying to do is understand from the very first principles of the quantum field theory what the emergent phenomena is from QCD. What does QCD actually predict for our universe? And what insights into how our universe works can we obtain from that? The reason it's an interesting, complicated problem is because empty space is actually unstable to being empty. That costs a lot of energy. And what it prefers to do is have quark and gluon field fluctuations in empty space. And I know you're thinking, wait a minute, I can't see these things. How do I know they're there? Well, you don't, because the photons that enter our eyes and allow us to see don't actually directly couple to those gluon fields that are filling empty space. So let's try and understand what that gluon field might look like. You see, photons mediate the interactions between charged particles. That's how one charged particle over here knows that another charged particle is over here. They're exchanging photons between them, and it's that process that gives rise to things like opposite charges attracting each other. Gluons do the same thing, but whereas photons don't carry the electric charge, gluons do. And as a result, gluons can directly interact with other gluons. And they can do that in two different ways. There's a diagram here on the left that shows a gluon coupling to two other gluons. On the right, we have a four-gluon interaction. One comes proportional to g. That's the strong coupling constant. It's like the electric charge in quantum electrodynamics. It's the strong coupling in quantum chromodynamics. And as a result, it's this unusual interaction that gives rise to empty space not being empty. Now, how many gluons are there? You can see that they're composed of a color and an anticolor. It's a nice way of thinking about them. And you might be thinking, okay, that's 3 colors, red, green, and blue, times 3 anticolors. That's 9 gluons. But one of them is a color singlet. Red anti-red plus green anti-green, blue anti-blue. That one doesn't count. And so there are actually 8 colored combinations, or 8 kinds of gluons. Let's take a look at the proton mass and how that comes about. You need 2 up quarks. Up is a particular flavor of quark. You need 2 of those, and they have 3 MeV mass each, so we're looking at 6 MeV. You need 1 down quark that has a mass of about 5 MeV. Added up, you've got 11 MeV, but there's a problem. The proton's mass is 940 MeV. So you've got to be asking, where's that 99% of the mass? It's missing. And where does it come from? What is the origin of the proton's mass? Well, to answer that question, we have to take this field theory, quantum chromodynamics, and put it onto a space-time lattice. So the idea is that the gluon fields, at each point in space-time, you'll have a gluon field the gluon field is a vector field, so you need to associate a direction with it. So it's actually the links that the gluon field sits on. Because there's 8 gluons, each link is actually a 3x3 complex special unitary matrix that has the 8 degrees of freedom that we need. Now, I've only illustrated a very, very tiny lattice here, 5x4x4. Typical lattices these days are 32 cubed by 64, and so we're talking about a lot of sites. Let's think about the computational budget associated with handling that kind of data. You've got that many sites that you need to look after. There's 4 directions for the vector field. There are 8 electric fields, and there are another 8 magnetic fields. Multiply it all out, and you're looking at 134 million degrees of freedom. Now, it turns out that what we're trying to do here is actually do an integral over each field. That means we're trying to do a 100 million dimensional integral. And yeah, that's hard. So as a result, we spend a lot of time paying attention to the TOP500 performance index. This is an index that started back in the early 90s. And what you're looking at here, on the x-axis, the year, and on the y-axis, the Rmax performance. What is that? It's the real performance that a supercomputer demonstrates when it's solving standard linear algebra problems. The units, in this case, gigaflops, which means 1 billion floating point operations every second. So that's 1 billion multiplies, divides, adds, subtracts every second. That's the original unit. Now, as time has passed, we started in the gigascale era. Very quickly, we were up to the terascale area here in the late 1990s. Then we hit the petascale. Here's the top computer, the first in the list, hitting petascales back here around 2010. And of course, the next scale is the exascale. And you can see that we should be looking at exascale in 2020. Now, it would be lovely to be number 1, but to be in the top 500 lists, you need to pay attention to the 500th, and here it is in blue. If you want to be in the list, you've got to be above this curve. The other thing that we like to look at is the sum of all of the computers between the first and the 500th, and that's plotted here as the green line. Now, the rate of growth is particularly important. You're looking at typically 1.8 per year. That means that the speed of supercomputers is almost doubling every year. If you don't keep up with that, 3 years' time, you're a factor of 8 behind, and that can be problematic. What about the academic and research sectors? Well, here's the academic sector here in blue. We've got the research sector in red. We've got the sum here in dark blue, and then the sum of the top 500 in green again. So what can you take home from that? First of all, academic and research sectors, they do track that trend of the top 500 sum. And in fact, these sectors are the ones that dominate that top 500. So who's in the top 500? When I'm asked, I like to refer back to the June 2016 list. Of course, the reason being, I get to say the University of Adelaide was in it. But we have very good company. You'll find University of Tokyo, Edinburgh, Purdue. Well, there's lots of good company. In fact, there are 94 academic institutions in that top 500 list. You'll also find some real powerhouse research institutes, like Riken with number 5 in the list. Jülich with the Jew Queen at 14. POSI comes in at 79 with Magnus, and Rigen's there from the NCI at 99. And Victorian Life Sciences Computation Initiative is also there. Here's the Magnus supercomputer at the POSI Center, 35,000 cores plus, delivering 1.5 petaflops, serving Australia. It was 58th fastest in the world when it appeared. Here's Rigen, 72nd when it appeared, 1.1 petaflops, serving Australia. And recently it was just upgraded. And so on the June 2017 list, we see it's now 70th in the list and serving 1.7 petaflops for Australia. Here's how these Australian national resources fit into the top 500. Again, we've got the 500th here in blue. We've got the number 1 in the list in yellow. And the orange takes care of the Australian supercomputers. We started off with the SC quite some time ago, well within the top 500, a very nice machine. And as it was getting old and close to the 500th, along came the AC, and that again was a very nice machine, but you can see that it lived far too long. Fell out of the top 500, and in fact, in early 2010, 2011, this was a very dark time for supercomputing in Australia. You were trying to serve the nation's need with a supercomputer that wasn't even in the top 500. Fortunately, that was addressed with the introduction of VAU, followed by Rygen, and now Magnus running alongside Rygen. And then there's also the recent upgrade here. It's a different story, though, for how much of this compute power was delivered to Lattice QCD. In the good old days, you can see that we would get about 10%, right? 1 decade down from the whole machine, about 10% for Lattice QCD. But when VAU came along, you can see that there was a jump of a factor of over 10, and yet a very small increase in Lattice QCD. We went from 10% of the machine to the order of 1 to 2%. The reason for this is that the funding model provides only a small proportion of these machines for the national merit-based allocation, and that is a problem. And I'm pleased to say that we're making some progress towards resolving this, but much more work needs to be done. So we look to South Australia. What can we get locally? How can we make up for this gap that we're missing? So here's the South Australian resources in the context of the 500th and the top 500. Back in the good old days, back early 2000s, we had Orion. It was the national facility for lattice gauge theory. It meant that we had the whole machine to ourselves, and that was pretty great. Shortly after that, Hydra came along. It was a teraflop computer, so we were excited about that. It was complemented by Aquila. So again, South Australia had supercomputers in the top 500. And then you can see we ran into the same problem, that these computers were left running for too long. They weren't upgraded. You fall out of the top 500. Corvus came along and just squeaked over the line, but then survived way too long. Eventually, Tizard got close to the top 500, but there wasn't enough investment to get us back to where we needed to be. Then we had problems with equipment failure. Phoenix came along to save the day to some extent, but we're a long way away from the top 500. And it was the University of Adelaide stepping forward, investing over $3.5 million into South Australian computing to get us the Phoenix upgrade, which put us back well in the top 500 again. And of course, we're very concerned. What's next? We need to keep investing. If we're not in the top 500, we're in trouble. How much of that has been allocated to Lattice QCD? That trend line is very much below where it needs to be. I'm happy to say that we're on the high side of the curve, but it's a problem. And so when you put it all together, Lattice QCD resources in Australia, compared to the top 500, we're not where we need to be. We need to be here. But we're doing fairly well. We're within a factor of 6, and it's a lot better than a factor of 30 that we were dealing with back in 2011. Okay, so there's a tremendous need for speed. If you're falling behind by a factor of 6, you've got some trouble. What other people can do in a day, it takes you a week. What should be done in a month takes half a year. And look, you can handle that. If you've got a good idea, if you're doing innovative work like the ARC asks us to, you can cope with that. But it's harder if you had a 6-month calculation, because that's going to take you 3 years, and that's probably too long. Fall behind by a factor of 10, which is not unusual. 3-day calculation now takes you a month. What others do in a month takes you a year. This is problematic. 6-month calculation is going to take you 5 years, so you won't even consider it. Factor of 30, what others do in a day takes you a month. What should be done in 2 weeks now exceeds a year. A 6-month calculation would be 15 years. You can't even play the game at this point. So, need for speed. You really can't fall behind. If you're doing future planning, trying to select the next generation supercomputer, if you're not planning on being in the top 500, then you are planning to fail. How do we survive? We've got this factor of 6. There are additional resources that have been very valuable to the group. One particular case was the IVEC Petascale Pioneers program. Back in 2014, they had large amounts of CPU hours that we needed to use in a short period of time. That's perfect. We can help you out with that anytime. Just give us a call. We've also benefited from the Galaxy Supercomputing Time Grant. Another thing that the POSI Center has is the Slurm batch scheduling system. It's very, very clever at fitting smaller jobs into that machine so that they can run, be in bonus time. And the other thing is that they have soft limits on those allocations, so bonus time is good. The Athena Early Adopter Program is going on right now, and we're benefiting from that, not only from the extra resources, but actually being able to provide feedback on our codes, how they perform, and giving advice on what that next generation supercomputer should look like. I'm often approached by people saying, well, what about this system? You know, you could get these for this particular dollar per CPU hour. But it always takes me back to my supervisor back in 1989. His favorite saying was, if you have to pay for it, you cannot afford to do it. Neil Tyson has a nice quote here. He says, science is for anyone who's curious and wants to invest there. And we hope that Australians remain curious and encourage our governments to invest strongly in science in general. Not only do you need investment, but you need talent. And fortunately, we have lots of talent here at the University of Adelaide. Professor Tony Thomas was a laureate fellow. Russ Young and James Zanotti were both future fellowships. Wasim plays a particularly important role in the group through algorithm development and the implementation of those algorithms on the latest architecture that might be available to us. We're also supported by postdoctoral research associates, recent PhD graduates, and a great number of PhD candidates and MPhil candidate. We're all benefiting from very substantial resources through POSI and the NCI. I want to highlight two of the students, Josh and Finn. I'll be talking about their research as we go forward.